Hello, quick video looking at the trends in ionization energy across periods. First, let's have a quick look at the evidence that gives us ionization energy. If you pass an element through a mass spectrometer, you vaporize it first, and the individual atoms in the vapor are ionized by an electron gun, creating 1+ ions that accelerate through negative plates and pass through an electromagnetic field before being amplified at a detector and then converted into a chart, or a spectrum as we call it, by relevant software at a PC. So if we run a separate mass spectrum for all the elements across a period, you can get a graph that looks like this. And you can see that you've got dips and troughs that can only be explained by the use of orbitals and subshells as a model, which supersedes the original shell model that Niels Bohr came up with in the 1920s. So let's look at some general trends first, period 2 and period 3. The general trend is upwards, and what's happening is the nuclear charge increases. You can see the number of protons plotted along the x-axis at the bottom. As the nuclear charge increases, but the shielding stays the same, the attraction of the nucleus to the outer shell electron goes up, so it becomes harder to remove that outer shell electron. Let's look at a few of the anomalies. So firstly, helium going down to lithium. If we compare the two electronic configurations, you can see lithium's got an s1 electron in the 2s orbital, and that's shielded by the presence of the full 1s orbital in the first shell. So let's have a look at that in another way. This is our 2s1, and this is our full orbital underneath it, in shell number 1, and that's shielding the 2s electron from the effects of the nuclear charge. So therefore it's easier to remove that electron. Let's have a look at another one. Same story here, 3s1 and sodium that is being shielded by a full 2p subshell underneath. And if we draw the equivalent diagram for that, this time round the full 2p subshell is shielding the 3s1 electron, so therefore it's a little bit easier to take away that electron, hence the drop of sodium. Same story at potassium, 4s1 being shielded by the full 3p subshell underneath. So you don't need a picture this time, I'm sure you're getting the idea. Let's look at lithium going to beryllium. What's going on here is at beryllium and at magnesium, you've got an s2 configuration, so an additional electron with no extra shielding, but one extra proton, 4 in beryllium and 12 in magnesium. So if we look at sodium, you can review that electron is easier to remove. But if we now move it on to magnesium, you can see that the electron, this one here, is harder to remove because you've got 12 protons instead of 11, but the same amount of shielding. Beryllium down to boron, a slight dip there, same dip from magnesium to aluminium. So the story this time round is that p subshells now being filled in each of those two elements. So let's look at boron as an example. You can see a p subshell starting to be filled, and that p subshell is shielded by the effect of the full 2s orbital beneath it. So going from boron to carbon to nitrogen, same story over in aluminium, silicon and phosphorus, a smooth increase this time round, because as the p subshell fills, the electrons drop into separate orbitals and therefore avoid repulsion, like this. So we've got 2p1, 2p2 for carbon, and 2p3 for nitrogen. These electrons are not suffering from any repulsion. You get an increase in the number of protons, so therefore the ionization energy goes up due to only one thing. Going from nitrogen to oxygen, a little bit of a drop here. So still in the p subshell, what's happening here is the fourth electron has to drop in next to one of those other three. So now we'll have an orbital that has 2 electrons in it that will be repelling each other. So this is our p4 configuration for oxygen. This electron here is actually suffering from a bit of repulsion, so therefore it's easier to take away. So the ionization energy drops again. Going from oxygen through to fluorine through to neon, and sulfur through to fluorine through to argon. Similar story, a new electron is added to a p orbital, and what happens is identical repulsion compared to the others, so same shielding, so the major factor this time is the extra protons. Thanks for listening, until next time, see you soon.